Alright, welcome back. Okay, so in this video we're going to be doing something exciting. We're going to be diving into the code itself of the implementation. It's called the breast cancer diagnosis. This code shall be uploaded as well. I think I will prepare a GitHub repository for it as well. So yeah, I suppose we'll just jump right into it. And yeah, first of all, we have the libraries, right? And I think I have already explained about the library stuff in the beginning. And then let's just jump right into this. And this bit of code right here shows like the first 5 rows, and this one the last 5 rows, right? As you can see here, the data set is actually not that big. Like there are actually 569 uh, data uh, data rows, right? But we have so many columns here, as previously explained. So yeah, perhaps if you are unaware of how the data looks, perhaps you can actually just go back and refer to the video. Okay, so okay, next up, we have this bit of code right here. So the purpose of that code is essentially to try to drop um, the ID column for this bit of code right here, and then we're trying to also drop like those columns which are unnamed as well. And then after we drop it, it looks like this, right? So previously it has an ID column, so now it doesn't have any ID column, right? Okay, okay. And then we do a label encoding on this. So previously, the diagnosis column consists of like two values, right? The malignant represented by M, and the benign represented by B, right? And essentially, okay, wait, my lighting is not working. Yeah, okay. Let me just, okay, I suppose that's better. I'm looking, okay, that's good. Okay, let's continue. So, malignant and benign, right? And we try to do a label encoding here. So we label M to 1 and B to 0. And there you go. It's actually changed in the diagnosis stuff, in the diagnosis column, right? Okay. All right. And then we are assigned um, the X values to the X variable, and then the Y value diagnosis, right? The actual like so-called output, I suppose. You know? Yeah. And then here we're trying to actually just find for missing values, right? And luckily the data set is actually very clean and no missing values is present, and therefore we don't have to do any data um, like we don't have to like fill missing data, right, with any method. So yeah, as you can see right here, no missing values, right? No missing values, no missing values. So it's already very clean from the way I got it. Oh yeah, basically I will also try to share the dataset as well. So yeah, okay. So next up, we try to look at the representation of data itself, right? Okay, so essentially, uh, yeah, the ones that are malignant is less than the ones that are benign, right? So a lot of the time the data is actually benign, and in balanced data, our models can actually be biased if they are actually trained in imbalanced data. It is actually going to be balanced towards the class which has a larger amount of data. But in our case, even though the data is imbalanced, the imbalance is not significant enough that we have to actually do some um, yeah, some sampling methods. So yeah, we can actually just leave it be like this. Okay, so here we're trying to do the train test split. The ratio I choose to be 0.34, and then we just directly apply some some algorithms, right? Okay, so first of all we have logistic regression, and then we try to get the scores. So the scoring shall be based on accuracy, precision, recall, F1 score, and the AUROC essentially. And It's got to be cross-validated, and I shall actually explain about cross-validation in the next video. But in this video, I just want to show you the code, like how it looks like. So here, essentially, we are able to get the fit time, the score time, accuracy, precision, recall, F1, as well as the AURC, right? The RC value, right? And then the code below that, the next up, we are actually just trying to plot the um, AURC curve, right? So as you can see right here, on the y-axis we have the true positive rate, and on the x-axis we have the false positive rate, and this is how it looks, right? And then you have the value as well for logistic regression. Okay, okay, and then we also have that for decision tree. It's pretty much the same essentially. And yeah, as you can see, like it has a lower value here for decision tree for AURC, right? Okay, so as you can see here, the X label, Y labels as well. Like the X label is false positive rate, the Y label is the true positive rate, right? And then yeah, okay. First of all, I'm so sorry. I prefer the dark mode, right? So technically, you can just change it to like light mode. Wait, how come it's not working? Okay, I suppose dark mode is already applied to it, so I'm so sorry if it doesn't look very clear. But yeah, essentially this is a true positive rate on the y-axis, false positive rate on the x-axis, and then we have the RC plot title right here, right? So yeah, we also apply that to SVM, so we have SVM right here, so it's the same as well, and then LDA, QDA, next up, right? And then we have last but not least random forest, right? Okay. Oh, sorry. We also have KNN as well, and base, knife base, right? Okay. Right. Okay. So here, what I'm trying to do right here is actually to try to like summarize, right? Provide a summary on like all the models, fitting time, scoring time, accuracy, precision, recall, F1 score, and AURC. And what I did here was that essentially I tried to compile all the models, right? So the model we used are the logistic regression, decision tree, SVM, LDA, QDA, random forest, and KNN, as well as naive Bayes, right? Okay, and then I just compiled everything, every single performance evaluation methods, right? And here, so we have all the fitting time, scoring time, accuracy, blah, 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 and then I just state everything for every single model, and then I set the columns here, right? The model, fitting time, blah blah blah, and then I try to actually sort all the values. I actually try to sort the model, right, by accuracy. Okay, so in this summary, you can see here is that the value is actually descending, right? So because I set ascending to false, right? It's to false, right? So it's actually ascending, but for other scores, such as let's say the precision rate, it actually goes up and down. So it goes up and it goes down, you know. So yeah, it's actually not sorted, and because of this, it's actually very hard, right, for us to like um, try to compare, because we're going to be dealing with a lot of comparisons, right? So like from one performance evaluation methods to another, and then we're going to look at the results between when we do dimensionality reduction versus when we do without dimensionality reduction. So like I decided to just do this model, right? So do it like um, do one of this for every performance evaluation method. So this one is for accuracy, and as you can see here, it's also descending, right? And yeah, and usually, like for example here, the uh, random forest for some reason comes up on top in my results. And so yeah, the second place it is for accuracy is LDA, but this one is logistic regression, you know. And yeah, um, This is for recall, precision, and this is for M1 score, and this is for yeah, this this is for AURC, and yeah, okay, and this is just the area, the ROC curve, right? But uh, I want I wanted to combine it to see whether or not it is actually um, you know, possible to see like any clear to see it clearly, right? But turns out, you know, it's very jumbled up, and I don't recommend using this. So I suppose we can just skip that, right? And then in like the next video, after I explain about cross-validation a bit, I'm gonna be talking about dimensional layer reduction, and we're gonna look at the code itself, right? And in this video, we're gonna be using the correlation coefficient to select like which features are gonna be used, right, for the models. Okay, so I suppose that's it for this video, and I'll see you in the next one.